morning. And then share screen. And I want to start off with this morning. Sam, can you see that? Sophia, can you see that? An article?
Yes.
Okay, so I'll actually sit and talk about this. This is an article that came out on the 12th, actually, of this month, and it's talking about the importance of lightweighting cars, even though we're switching to electric vehicles. And I thought this was pertinent. Because I think it puts some significance on what you're learning here and how applicable this is, and you know, not to be, you know, too self-important, the importance of lightweighting and what it really means for sustainability and climate change. So I highlighted some stuff here. The article is written by an economist. So this is not an engineering article. It's not going to talk about the wonders of carbon fiber in here or titanium corrosion resistance or anything like that. The article really kind of equates like lightweighting to societal costs. How much does it cost in terms of people, in terms of climate change, floods, etc., to stick with such heavy cars? And morning, Tyler. There's some interesting things in here about that cars like sedans and, you know, little coupes and things have increased in weight by 12% since 1990, and for pickup trucks they've increased by 32%. And he's saying that they're saying, there's a couple of authors, they're saying that when you go electric, it's a problem because the vehicles become much heavier. So he takes the Ford F-150 pickup truck. So the Ford recently announced that they're going to come out with an electric version of the Ford F-150 pickup truck. I think they're calling it the Lightning. And the vehicle is 700 kilograms heavier than the petrol version, the gasoline version. So that's a big increase. And there's similar kind of percentage increases with cars when you go from electric, or when you go from gasoline powered to electric. And he goes on, or they go on here to equate those increases in weight to costs for people getting killed. If you know, in an accident, that there's some relationship he's drawn between the mass of the vehicle and the likelihood of somebody getting killed in an accident, or a pedestrian getting killed in an accident. And then they talk about the effects of weight causing more particulate matter in the air because of tire wear, which is an interesting point. So when you drive your car down the road, these little pieces of rubber come flying off. Most of the time, you know, you don't see them, but little tiny pieces of rubber, you see them stick to the road. Apparently there's a nonlinear relationship there, that as you get heavier, you get disproportionately more little particles spewing off your tire onto the road. That's another reason. And then they talk about the idea that there's more material in the vehicle, there's more energy that goes into making those materials, and therefore, in some instances, depending on what you're burning, you'll actually negate the advantage you get from using an electric vehicle because of the increased mass. So he challenges the US government and the auto industry to start thinking more in terms of lightweighting. They talk about taxing vehicles based on their weight, which apparently they do in New York State and they do in Oregon already. I didn't know that. And then there's a nice graph here that shows the relative weight difference between electric vehicles of the same car and gasoline powered versions. And he talks about lightweighting frames. So that's what we're talking about here, about one of the ways in which we can mitigate this problem is to make lighter vehicles. So I just wanted you to see this article just to understand how germane lightweighting really is. And there's things that you'll probably learn here that can really go out and help the world. So just think about that for a second, okay?
Was the truck percentage that trucks went up 30%? Was that like all trucks or just?
It was pickup. It was specifically pickup trucks. So
I'd be interested to know how much of that is, because there aren't like medium, small.
I know,
trucks
right?
anymore.
Exactly.
So how much of it was stack shift versus like taking the same general shape? And it
Right.
being
Yeah, when I was a kid, there used to be like small and medium-sized pickup trucks, right? I mean, they had pickup trucks that were like the size of a smart car.
Well, I mean, even just the ones that are like slightly bigger than stick-ons.
Right. Right, and now they're all F-150s and Ram Super Duties and big Silverados and you know, you're right. It's a good question. How much is convoluted in there between the actual changes in structural efficiency and just having a bigger car or a bigger truck? It's a good question. It's critical thinking. Okay, so anyway, you guys, if you're interested in this article, it was in Nature and volume 598. I don't know how this says. I guess this must change every day because I could swear this said the 12th the other day. It's right here, the 14th. You guys see that? Anyway. Okay, let's get to our lecture then. Okay, again, guys, if the screen isn't moving on your side, let me know. It must mean I have multiple versions up or something. So just to take a step back, what we talked about last time. Talked about, okay, we compared two bicycles. I said, these bicycles are both made out of steel, yet one is significantly lighter than the other. How did that happen? It happened because it took advantage of both materials improvements and because of geometrical improvements. We talked about the modes of loading. There's tensile, shear, double shear. There's buckling, bending, torsion. And we talked about how when you have these different modes of loading, how the stress is distributed across the cross-section of a beam that's in one of those modes of loading. And we realized that we could use that distribution of stress to our advantage to increase or at least maintain the sort of stiffness or strength of a beam, but at the same time reduce weight. And we do this when things are under bending or torsion or buckling by growing the outer diameter of the part or the outer dimensions of the part and then thinning the wall. It's a tube. And that's exactly what they did in those two bicycles. They went to a bigger diameter and they thinned the tube out. And we talked about these constitutive laws of mass savings. Okay, that there's equations that I came up with. It's no fancy derivation by any stretch, where you can plug in different values of the material's stiffness, density, strength, Poisson's ratio, and then you can begin to estimate what's the relative mass savings compared to using different materials. And we said that this has to be under the context of the mode of loading and whether you're designed for stiffness, okay, or designed for strength regime, right? So sometimes when you're designing a part, you'll dimension the part so that it meets a certain strength. That's your requirement. And then sometimes you'll dimension a part to hit a certain stiffness. Robin was telling me before you guys got here. You want to tell Robin or should I?
I mean, I think if you want.
Go ahead.
My background is in civil structural engineering.
Okay.
And a huge amount of buildings is also governed by stiffness rather than strength, especially floor beams. Floor beams are based, like how many there are and the spacing between them is all based on the deflection, because humans get really freaked out if a floor is bouncy. Like it's literally based on comfort. That all of your floors could have like I think maybe up to like half of the material that they currently have, but you would kind of like move every time you walked on it, and it's not a fan of that.
Right. So even like sitting like on a bridge, in an overpass, like this
Oh
morning.
yeah, when a truck goes by and
Yeah.
goes for 10%.
Yeah, this morning I was waiting in the, where you go from the Pike onto Starro there. There's that off ramp, that horrible off ramp, and I'm sitting there and like things bouncing. It's unnerving.
Yeah, people don't like that, but it is actually safe.
Just even with cement.
I mean, you'd be surprised on how much it can move, and also like with bridges, there are joints. So
Yeah.
like the whole thing is probably moving to a certain degree. Like it's probably a little bit more like that kind of action,
Right.
Versus the cement.
Okay, that's good to know. So there's an example.
It's also important to know that the cement is there just for the compression side, like, and to hold the rebar there.
Right.
So like.
They don't rely on tensile.
If there's a huge crack in your cement underneath the bridge, it's a bad sign because it's designed not to do that, but the strength of the bridge hasn't actually decreased until the rebar has decreased in literal size to your rest.
That's bad. And it's interesting, if you look at the cross section of bridges, a lot of the ones I've seen, they actually bias it so it's smaller on the bottom of the beam, right? So they have less cement than a tensile. Is that right? I'm just
So
speculating.
yeah,
here.
so like literally, like if you do you want me to doodle?
Sure.
So like if you look at
There you go.
Like a piece of reinforced concrete. If you're loading it on top and then bending, you only need rebar down here, and all of this concrete does nothing.
Does nothing.
You don't use it in any calculations in any way.
It just transfers.
So
the
you
load.
use this for compression and you use this for tension, and that's it. All of the concrete in here is just to hold the rebar to the rest of it.
Light weighting is only important in this case, in as much as it relates to money and natural frequency, right? More material is more expensive.
Yeah, money's the biggest bit, and then you want to get into environmental.
So I've seen bridges that have a cross section that kind of goes like this, because you don't need much cement down here. I guess, right? Yeah. Okay. See, we derived, or I told you guys could go back and look at this if you wanted to derive the equations for these constitutive laws. You can derive this fairly easily. The derivation is in here really only to show you guys if you find something you want to try on your own, I don't know, some loading condition, and you can do the same thing. So you know how the calculation goes, but it's pretty simple. If you write out the equations of, in this case, bending and strength, and then you have that for one beam and a second beam of different materials. You can equate those together, cancel things out, and then have it a combination of the H's or the thicknesses of the beams, and then you can relate those H's to a mass, right, of the beam through the easy geometrical equation for mass, times volume times density, basically, and you can just solve this through. It's pretty easy stuff. We plugged in properties for different materials to see what would happen, and the big surprise that came out of this is that sometimes you can actually design things lighter out of steel because it has such a high stiffness. That was surprising. Everyone always jumps to aluminum or magnesium when they want a lightweight. They don't think it's steel, but sometimes you can actually do lighter with steel. And this is when you have things that are loaded in tension or compression or shear, not necessarily for bending or torsion or buckling, but for just simple tensile or compressive loading. Sometimes you can make a lighter structure out of steel. We talked a little bit about packaging, that even in bending, sometimes you're assuming that you have enough room for packaging so that you can grow the outer dimensions of a structural member. We talked about door inner beams where there's not enough room in there to package a big beam. So you can't make that out of aluminum, even though it's in bending and have a weight reduction. So they're often just made of steel because you're interested in absolute strength and you're very constrained as far as how much packaging space you have to put the beam. We talked about a little bit about Ashby diagrams. Ashby diagrams are just a graphical representation of the constitutive laws of weight savings. We talked about body structures of real cars, that you can break the body structure of a car. If you think about it into a series of beams, hollow beams, and then under different loading conditions. So for the whole vehicle, front impact, rear impact, bending, side impact, torsion, you can begin with finite element analysis or just through intuition to assign different modes of loading and to each of these different beams in the body. And then you could say, wow, this one's only under compression. This one only sees tension across all these different loading conditions. Therefore, making that part out of aluminum or magnesium or carbon fiber would probably be a waste of money. And I can make that part lighter and cheaper if I make it out of steel. Don't always negate steel. Okay. Any questions on last week's lecture? Guys, everything good? Okay. So last year was the 2020 annual meeting for Tesla was they called it Battery Day. Anyone watch it? It was a lot of fun. It was a lot of fun. I always enjoy watching Elon Musk. He's so articulate. Interestingly, they talked a lot about light weighting in this annual meeting, for investors, which is kind of surprising because usually they just talk about financial things, but this time they decided to call it Battery Day. And they talk a lot about light weighting. They talked about metallurgy. Elon Musk talked about batteries and how to make batteries smaller and lighter. And there's a couple of things here that were interesting, I thought. He talked about making the body structure out of single piece large aluminum caskets. In fact, Tesla has invested in the largest aluminum die casting press in the world, the Gigapress. They developed actually new alloys that didn't require heat treating and still had sufficient strength. So typically, like we talked about in the first couple of days of this lecture, we talked about precipitation hardening. We talked about how you go from, making aluminum whatever 30 KSI material to a 60 KSI material by heat treating it. So when you injection mold something or you die cast a big aluminum part, traditionally you've had to heat treat that part in order to get the strength out. You have to solution treat and artificially age. But the issue there is that when you have a big gigantic piece like this with really thin walls, the part gets all distorted. And then when you try to put the car together, nothing lines up. The car looks like heck. The door gaps are all over the place. Things hit each other. It's a mess. So you can't have that distortion. So Tesla, using integrated computational materials engineering methods, under Charlie Kuhlman, designed a new aluminum alloy that would be sufficiently strong, fresh out of the mold, rather than having to heat treat it. And that's, I think, gone into production in the model. I get the Y and the X confused, which is the sort of small SUV is I think that's the Y, and the big SUV is the X. Anyway, so when this came out, a lot of me and my geeky friends were really excited about this. So we poured over this information, and we came across something that's kind of interesting. This is the, so here's a picture of where this rear casting goes. It's the rear wheelhouse pickup, where the spare tire would go. And then here's that part, I guess, on their launch vehicle, or their launch vehicles. And you can see this is one aluminum casting right here, okay? You can see this web structure right here. That web structure on my beam diagram would be right here. Does anyone see anything kind of, if you think about the modes of loading and the stress distribution, and you think about this body being in torsion, you see anything that might not be optimum there?
Which way?
So imagine that you were holding the car like this and you were twisting. You've got all these web structures here.
So like in and out of the page?
Yeah, you would be twisting like this.
You don't have anything on this edge. It's like a tube, so that's the thing.
Exactly. Got it, Robert. Exactly right. So I don't need to be critical of Tesla here. I'm a big fan of Tesla. I admire what they do. They offered me a job once and I turned it down because I thought they would fail. Pretty stupid, huh? But this is exactly right. So they have where the loads would be the highest in torsion on the outer skin of, it's effectively a tube. They've taken the material off. So they've taken material off where the stress would be the highest. And the way they have to make up for that is probably by putting more material inside in order to get the stiffness back. So they probably did this because the way they cast the part, I don't exactly know what they did, but they cast it in some orientation where probably they have to take the mold out of there, and if it were closed off, they might be die locked and they won't be able to get the part out. So I'm sure that the engineers at Tesla thought about this, okay, and they had a compromise. They had a compromise to do this in order to make this part out of aluminum. But every engineering design has some compromise. Always, you'll never make a perfect part. But it's interesting to see what their compromise was, that they would open this up like this to take away some of the strength and stiffness. Robert?
Do you know what the strength is?
I do not know. I do not know that. And he did talk about it. Huh? Yeah, Google it, yeah.
Do you know what it's called?
I don't know what they call it. He's probably got some snappy name for it, like all his products, it's got a snappy name. The Gigafactory.
I'll see if it comes up quickly.
You might, it might help if you look at like new aluminum alloys, Tesla Model Y.
It's in megapascals.
Okay, what is it in megapascals?
And 175 megapascals.
So you want to think in KSI?
Yeah.
So that's the yield strength or the ultimate?
Yield.
Yeah, okay. 175. Okay. That's 25.4 KSI.
That's pretty good because 606126 is like 35.
Yeah, right, exactly.
Or
Exactly.
so.
Right. So that's not bad for casting. I've certainly, some of the other casting alloys like A356 is nowhere near that strong. So that's not bad actually. it's not bad. The guy put this in reference, guys. So like a 70-75 aluminum may have a strength of 50-60 KSI. It was 56 KSI, but 70-75 was in the T6 condition. Some of the steels we deal with, the really high strength steels, they have like a what's that number? Like over 200 KSI yield strength. So just give you an idea of like aluminum compared to what you can do with steel. This is an explanation of that. It's interesting. He talked about in that day. He also talked about the battery pack, using the battery pack as a structural member, and even a step further, using the individual metal cans that make up the battery. So the battery is like a metal can, and there's like they call it the jelly roll of anode, cathode, and the jelly in between. They stick that down in the can. Anyway, so there's a steel can, and basically the steel can stops the chemistry from leaving the can or leaving the battery cell. It stops intrusion of the battery cell, shorting, things like this. So it's got to be pretty strong when we make those out of steel, but they're heavy, right? So Musk talked about using those as structural members. So if you think about here's the front wheel, here's the rear wheel. You've got this battery pack in the center of the vehicle. Okay, got a roof that comes up over here. Good. Roof that comes up here. Okay, and so this whole thing, when you hit a bump, for example, is under bending. So that means that to some extent, this is probably more under a tensile and a compressive load, depending on which direction it's bending, right? But maybe because it's got some thickness, it's under bending on its own. Battery pack's under bending on its own to some extent. So if I have these battery cells in here, and then you have these two stress skins, you separate those out by a distance, and you're increasing that moment of inertia, that I in the bending equation. Remember that? So what is it? Stress is equal to M C over I, where I is like 1/12 H2. Is that right? Close enough? Christiane saying it's close enough. What? It doesn't matter. One of these is out of the page, one of these is in the page. So let's just say that this is B. Anyway, so by separating these guys out, and you increase this B, so you lower the stress. But how do you keep them from buckling? How do you keep them from wiggling into each other? You have to have some structural member there in order to keep them strength and sound separated. And Elon Musk was talking about using the battery casing to do that, which I think is really, really clever and the right way to go.
They call those composite panels, effectively.
Exactly, Sam. It's just like when you have like a carbon fiber honeycomb panel. You guys ever try to break one of those?
Just treating the battery cells like the honeycomb.
Honeycomb in between, right? I had in high school, I had a friend who was a racer, who used to race cars, and he had this very expensive Italian steering wheel I wanted. And I bet him, I had a piece of honeycomb carbon fiber board. It was about this thick. It was about ½ inch thick. It had carbon fiber skins. It had a Nomex honeycomb core, and it weighed nothing. It was like less than balsa wood. And he bet me he could break it over his knee. And I said, you can't do it. I don't believe you for a second. So we bet the steering wheel, and he couldn't break it. His knee was all blue. His knee was all black and blue by the end of the day, but he couldn't break it. So really strong stuff. Okay. So Lucian Schmidt. Lucian Schmidt is, I think, the father of structural optimization. He's the guy I think coined the term structural optimization, structural synthesis, geometrical synthesis. He's really the pioneer in this field. And what this is basically is it's linking structural analysis with numerical optimization. In modern sense, it's hooking a finite element code with numerical optimization algorithms. And I think he was the first to do this. He went to school at this fine institution back in the 50s. He worked in aerospace for a while, and then he became a professor here for a little bit, and then he transferred to Case Western Reserve in Ohio. And he was a professor there for a long time. Eventually, he moved to UCLA and he died in 2018. It really kills me because I took summer school in UCLA in 96? Probably, no, that's not true. It would have been 1992. Anyway, I probably could have met this guy. It really angers me that like I didn't know who he was. But he wrote several landmark papers in structural optimization. The reason I'm showing you this information about this guy is if you want to learn more about what we're talking about, we're going to talk about in the next couple of minutes here. I encourage you to go to the library and look up some papers from this guy, because some of the papers are really fun to read. And they really nicely explain how you search a design space, a new term for you guys, a design space to find the optimum solution for stiffness or strength or fatigue or natural turbulence or whatever. Let's see here. Anyway, so go look this up. He's got some great papers that are in the library, and they're pretty fun to read. Here is one of the examples in one of his papers. This is from 1980 paper he wrote in 1981. I think he did a lot of structural work, structural optimization for NASA. I guess he got a lot of his funding from NASA. So there's most of these examples in one way or another relate to some type of spacecraft or satellite or something that needs to be strong and stiff. So okay, where we go? So I'm gonna try to draw this. Here you've got a column, a tube, okay? And it's under a compressive load. It is going to fail by either global buckling first or local buckling first. So this thing is a diameter of D, it's a dot. The wall thickness is T, okay, and the length is L. The goal you're after is to minimize weight. Right? There's an equation, a pretty easy equation right there that calculates weight as a function of density and the dimensions of the tube. Pretty simple stuff, right? Okay. The variables you have to work with are the diameter of the tube and the thickness of the tube. So I want you to start thinking in terms of design spaces. We mentioned this a little bit in the materials part of this lecture. We talked about the design space, for example, being made up of percentage moly, percentage chrome, that's perfectly valid design space for metal. In this case, we're dealing with, you guys see that, or is it too small? Okay, so here we have, yeah, that's a problem. This thing is a wide angle enough. I think you can see that. Okay, thanks, Robin. So, and here you've got T on the vertical axis, thickness. You've got diameter on the horizontal axis. So this is your design space. You can pick thickness, or you can pick diameter. And the question is how do you make this thing capable of supporting these loads? Or I'm sorry, avoiding buckling. Okay, how do you make it? How can you make this thing the lightest and still avoid buckling, given this loading condition of P, some load P? And it's very straightforward to start plotting contours on this plot of weight. Okay, so let's see how this looks. It looks something like this. Okay, so these are different weights. These are constant weight. Constant weight contours. Okay, and downhill is this direction. I don't know if you guys can see this or not. Okay, so these are weight contours. This is downhill. So you want to pick a D and a T that go downhill, right? Because that's a lighter solution. Okay. So this is a framework you guys are going to see a lot of from here on in this lecture about design spaces. We call objective functions and constraints. The W in this case is the objective function. The objective is to minimize W. And then there's certain constraints. You know, the thing can only be so big. The tube can only go so thin. You know, it can't be made out of ice. These are constraints. Okay. One constraint is that the diameter of the tube has to be less than 4 inches. Okay, so let's say that's some line here. Okay, and then you say the wall thickness can't be below 0.02 inches. Because probably there's some manufacturing constraints. Probably if you try to go below 20,000th of an inch, you get some flaws, or it doesn't get a good finish, or it just tears itself up out of the lathe. So there's a constraint somewhere here, let's call it. Okay. Okay, so this is your T has got to be greater than 0.02, and D has to be greater than or equal to, sorry, it has to be less than 4 inches, right? So that means, given these two constraints, your design can end up somewhere in this box right here. Can I see that? But you have other constraints too. You have these constraints for buckling, which is a function of geometry, both local and global. Got that? Okay. So the constraint for Euler buckling, which is global, is given by, let's see here, it's given by this blue line right here. Okay. And that, I'm going to do my best to draw this. Wish I could color chalk here. That's going to be some curve that comes down like this. Dark, so you can see. Okay. In order to avoid buckling, the combination of T and D has to result in a stress, or an H, which is that direction of the line. So now you're constrained by this sort of half parabola here. See that? Right? And then there's the local buckling. The local buckling is a little bit less useful. It kind of goes like this. It's this line right here. Okay. So knowing that you're getting lighter as you go in this direction, you're picking D's and T's to get you going this way. This tells you that the lightest possible solution is actually right here. So actually, I've drawn that a little bit high. It's meant to be on the 0.02 line. So that is the lowest weight solution because it's at the lowest contour line that meets all those constraints. Constraints for the diameter, constraints for the thickness, constraints for local buckling and global buckling. Okay? Does anyone have any questions about this? This is a key concept that's going to follow you around in stroke optimization for a long time. Objective functions, constraints. Okay? Yeah, the local buckling curve is actually this red line. G2, so that's this line right here. So you have to be below it. Anything below it is no go. Anything above it is okay. So if you the way they do this is very clever. They equate the formula, the stress for local buckling, to subtracting the stress at the part and the critical stress for the material. And therefore, if that function goes to 0, then you have a no-go. You've broken the constraint.
Local buckling is that tiny red line on the side?
Yeah, it's this tiny red line that goes like this.
Does it follow along with the T2?
Probably not exactly, but pretty close. It probably has some, in real life, it probably has some curvature. I've drawn this by hand, so this isn't, I didn't draw this on Excel. But it's probably pretty close to following the 0.02 line. So what I did is I've taken this paper right here and I scanned the paper and then I traced over it in PowerPoint. That's how I get these graphs. It's tedious, but it looks, it's readable that way. So it might be better probably to do this in Excel maybe next time. To draw the functions in Excel. So we're going to go back here. Okay, no questions about this? Okay. Here's a more complicated example. Here you have, this is actually famous. This is the 3 beams for a spacecraft, some type of satellite or something. I can't remember what it was. And you have fixed points up top. Okay, and you have 3 beams. And they're connected at the bottom. And there's some loads, P1 and P2, which are roughly symmetric. You know that the diameter of A1 and A3. So A1 and A2, A3 are the diameter of those tubes. Okay, N is the distance from the connection points at the top to the connection point on the bottom. And you have the angle between them. So it's a pretty simple geometry problem at this point. And rho is density. The objective function is to minimize weight. The design variables, since you simplify this, you said A1 equals A3, right? So then you can say, you can make this a function of only A1 and A2. It makes it a lot simpler if you use that symmetry. So the weight is a function of density. It's a function of that length N, and it's a function of the diameters of A1 and A2. It's very straightforward now to calculate out stress. Stress is Ij, where I is the structural member and J is the applied load, whether P1 or P2. It's very simple. Go ahead and then write out the equations for the stress. You know that this material is only good up to 20,000, call it PSI, I think, in tension, and negative 15,000 in compression. Okay, so you stress you have in these beams has to stay within that range. That's the constraint. You can't go higher than 20,000 PSI in tension. You can't go lower than 15,000 KSI in compression, or PSI in compression. Those are your constraints. The equations are given here again for these functions H, which is the stress in each one of those tubes effectively. They have to be greater or equal to 0. The design space is A1 and A2. A2 is on the vertical axis, A1 is on the horizontal axis. And then again, it's very easy. It's very straightforward to calculate out the weight of these 3 beams, or these 3 tubes. And then you can plot those contours on this design space, right? Again, this is the way they did it here is they normalized it by density and that distance N. But going downhill is this way. So this is the reduction in weight. It's going that direction. Those lines are plotted out here, normalized by, again, the N and the density of the material. And then on top of this, we've gone ahead and plotted out these H's, the stresses for the different beams. So this blue one right here is H1. The green one is H2. And then this, sorry, the red one is H2 and the green one is H3. Got that? Okay, so you need to be this direction of the blue line in order not to violate your stress constraint. You need to be this direction of the green line, and you need to be this direction of the red line. So the red line clearly doesn't play a role here, but the green and the blue do. So the H3 and the H2, sorry, the H3 and the H1 stresses are the ones that are ultimately dictating what's going to be the size of this part, these tubes. The contour lines are really straight. So the point where you get the lowest weight is right there. Right? This is where you're above the blue line, you're to the left, I'm sorry, to the right of the green line, okay, and you're above the red line. And the point that's furthest down the hill, the weight hill, is actually right here. So this is interesting. A lot of times people say, oh, well, it's really easy to lightweight things. Just take everything and figure out, what's the, where does everything break? Like, let's figure out where all these 3 loading modes where everything breaks, and then that's called the simultaneous failure criterion. Let's just figure out the simultaneous failure criterion. And that's got to be the point where it's the lightest. But it turns out that's actually not true. That sometimes you can make a lighter overall structure by having something that's maybe thicker than it really would need to be if it was loaded on its own. Okay, and that's why the lowest point on the hill is actually right here. Here's the simultaneous failure criterion right over here. But it's actually right here. This is where the lightest point is. So don't assume that you can take each structural member on their own, calculate out the stress for those, and then figure out where it fails, and then add all that up, and that's your lightest solution. That's not always going to get you the lightest solution. Here's an example. This is a kind of an interesting example where you can get that, where it's actually advantageous to make one tube a little bit thicker. Does that make sense, guys? Okay. So here's sort of the generalization of this problem right here. This numerical optimization problem. You've probably seen this before. We'll go over it for fun. You have a mountain. The mountain is representative of some objective function, f. You want to maximize the function. You want to get to the top of that hill. That's where f is going to be the biggest. But you have some constraints. There's snow fencing on both sides of the mountain. And you can't, if you're walking up this thing and you're blindfolded, you can't go past the snow fencing. So suppose you're blindfolded, you don't know, you can't see anything, you've got a good blindfold, and you have to walk up this mountain, okay? But you don't know beforehand like where the top is. So somebody drops you off there, they spin you around, they get you disoriented, and they say, find the top of the hill. So you start walking in one direction, and you feel like you're going up. So that must be good. You're going up, you're going up, you're going up. You keep taking one step. Maybe you start taking, the same step with your feet, one step, two step, stop, one step, two step, stop, reevaluate. Eventually you walk into the snow fencing. You go, oh, I can't go any further in this direction. What do I do now? So you switch directions and you move forward and you say, do I still feel like I'm going up? Yes or no? And you say, okay, I am going up. So you start heading a little bit further up, keep walking, maybe you take bigger steps, smaller steps, and eventually you run into another piece of snow fencing. And then so on. You switch directions again and again and again until finally you get to some point where if you walk any different direction, you feel like you're going down. That is the local maximum. So this is very much like when you have some formula that maybe represents weight or represents stress or represents natural frequency. It's a complicated equation. You don't know, you're totally disoriented. You have no idea like what's up and what's down, how you're going to increase or decrease that objective function. And even more so, like you don't really know beforehand, kind of intuitively where the constraints are. That's what you're doing here. That's really, as a mathematician, a person who thinks in terms of numerical optimization or studies that field, you don't know where you're going. You're blindfolded on a mountain trying to find either a maximum or a minimum. So we're going to play a game. Okay. We have this equation. It's f of x. It's some objective function. Okay. This might be weight. This might be natural frequency. It might be money. How much is this thing going to cost? We want to minimize cost. Okay. Could be a lot of things. And we're gonna search this design space and try to figure out. You guys are gonna know. We're gonna try to figure out where the optimum of this equation is. So it'll come back. Okay. Okay. So somebody pick a spot in this design space of x1 and x2. Robin. X1 and x2 are two variables. F is a function of x1 and x2. Okay, so these x1 and x2 could be the diameter, could be the thickness, it could be the length of a tube or a structural member, it could be a B, a height in a tube and bending. So you're trying to find out, you're blindfolded, basically looking at this. You don't know where up and down is. So the way a lot of numerical optimization works is they just pick a random point just to start off somewhere. So somebody pick a point on here. You want to start here? Zero is roughly. Actually, I did this in Excel and put in 0 blew up. So you want to pick this point right here?
Yeah.
Okay, so I'm going to delete that. Take it, I'm going to delete that point. Okay, so the value of f of x at that point is 5.1. I'll tell you right now, that's
we have no idea what x1 is.
no, x1 here is 0.1, negative 0.1. So this is your design space, x1, x2. So this, I'll tell you right now, this is not the minimum of the function. But what direction do you go next? You can go up, down, or diagonal either direction. You can go left, right, up, down. diagonal. You want to go up? Okay. So you want to go right here? You want to step one or you want to step more than one? Okay, you want to go to here? That one? Okay, 5.9. 5.9. So you went the wrong direction. You're trying to minimize f of x. You're trying to find the minimum value of f of x. Here?
Upper left corner.
Here. You guys want to go here? Okay. Ooh, you're much higher, 30.9. You want to go over here? Here? 34.1, even worse. Christine, you want to go to the bottom right corner? This one, my right or your right? Okay. You're at 9.52, so that's better. For you guys? Bottom left? Okay. Over here? 12.7, you're worse off. So you see how excruciating this can be. There are, you guys want to keep going with this or? One more, someone pick one more. Here? That one, you want to do that one? 5.04, so you're a little bit better. So you see how difficult this is. When you have an objective function, for weight or stiffness or natural frequency, whatever it might be, it's you're in the dark walking around without a flashlight. Right? There are actually some I'll show you that. I think the minimum I think was right here. That was the minimum, 4.84. So there are ways to help yourself with this, to make this easier. If you're good in math, like for example, you'll notice that x1 is to the 4th power. So Christine's nodding her head. X1 is to the 4th power, so it must be the most dominant in this equation. So you automatically know that you got to probably go to the bottom of x1. Here's what the design space looks like. And you can see where we are, this 4.84 and where we went. Here's a zoom out of what that looks like, that function looks like. Okay. And then so think about what you did there, though. If you notice the steps you took, you picked a point at random, you chose some search direction, and you chose some search step. How far am I going to go? And then I think you start picking some random things again, which is okay, but that's usually not how an optimizer will work. And then eventually, I think I just told you this is where the minimum is. But you got pretty close, right? I think, Robin, I think your first step was that the closest we got. Oh no, we got closer over here. So x2 equal to 0.4. Okay, so think about this, guys. This is really what you're doing when you're doing numeric optimization. You're searching in the dark without a flashlight. You're using that to help guide you. So there are things called constrained problems and unconstrained problems. Pretty much, I think the world consists of constrained problems because you don't have infinity. You don't have the space up to infinity to look at equations. On the right, we have, I guess you could call this an unconstrained problem. And your first year calculus class taught you how to find the maximum or minimum of that function, right? You take the first derivative, you take the first derivative, you set it equal to 0, then you solve for the design variable, in this case, x. X is the horizontal axis, right? That gives you where the possible maximum or minimum are, the places where the x value will give you a 0 value for the first derivative. Then you take the second derivative and you determine if it's concave up or if it's concave down based on the sign. If it's concave up, you know that that's a minimum. If it's concave down, you know that was a maximum. So this is first year calculus. This isn't a big deal. Things get chunky or get difficult when you start constraining a problem because your minimum and maximum aren't necessarily going to happen at a place where the first derivative would equal to 0 right here. And this is where the mathematics community has developed some wonderful tools and methods to help you find maximum, what's called local maximum, local minimum. Gradient methods, genetic search, particle swarm. There are people in this world, this is the last thing I'll say, we're done for the day. There's people in this world, mathematicians, who really get excited about these things. They have conventions, and they go to these conventions, and each person brings their own special algorithm with them. And they have races to see who can find local minimum, local maximum of an equation or function, something. So the conference organizers say, here's the equation, you guys go at it, where's the local minimum, local maximum? And they have like call them drag races. This guy I'll introduce you to next time, Vanderplots, Eric Vanderplots. He is a master in this. He's developed all these computer algorithms that find local maximum and minimum of very complicated equations. So that's it for today. Any questions? Think about your experience trying to find the minimum in that design space I gave you. Okay? Think about how that went.
Thank you.
Thank you. If you have any questions, let me know.
Thanks, Don.
Awesome. Thanks.
Thank you.
At the top is dictating about how many lanes you want,
Okay,
or like the actual string could be smaller.
okay. I always thought it was because they were trying to minimize the amount of cement because they didn't want the cement compression. And then
You
they
are,
didn't want the
like,
cement tension.
you could just make it a box instead,
Right. But they spend more money.
but like for the most part, strength wise, probably not something that big, but like to fit however many lanes you want, you have to have it right on top.
Thanks. Remember that for next time. Have a good week.